Hi, and welcome to 9.4 Inelastic Collisions. We'll start this video by discussing what exactly an inelastic collision is, rewriting our law of conservation of momentum equation, and then I'll get into the problems. So if you really have no idea what inelastic collisions are, stay tuned in the next part, but if you just want to get to the questions, feel free to skip ahead. Okay, for inelastic collisions, you'll have two masses that are colliding. So maybe M1 is coming in towards the right, and maybe M2 is kind of like a sticky block is the classic thing, or like a lump of clay, really. Because for inelastic collisions, after the collisions, they stick together. Now, maybe the velocity is, maybe it's at rest, or maybe it's not at rest, maybe it's coming in the other direction or anything else. But let's just say it's at rest initially. So then after the collision, so this is initially, after the collisions, they stick together. So this is still moving along here, but now the lump of clay or whatever it is, now it's stuck on, and they're moving together with the same velocity. But how should we draw this velocity vector? What do you think happens if the initial velocity looks like this? Maybe it's coming in very fast, all right? Super fast. Now it hits, and now it's going to slow down, isn't it? You could kind of visualize it in your head. So we don't draw the vector as big in our diagram. So this is the final situation. They move off together as one entity with the same velocity. So now, you could think this is V1I and V2I, but this is just the final velocity. They have the same velocity. So how's that going to affect our equation? The equation is still the same. Technically, it's still the initial momentum in the beginning. The total momentum of this plus that initially is equal to the final momentum of these two guys together. What is their momentum? Momentum is conserved, so it's the same. It should be the same quantity, right? So when you're writing this, okay, the initial momentum, initially there's two separate objects. So just like the elastic collisions, we have two separate terms, but we named them M1 V1I and M2 V2I. We're kind of skipping this step here. Hold on. Where does this M and V come from? In case you're wondering, we're just writing the momentum of the first one initially plus the momentum of the second one initially, because P is equal to mv. The momentum is equal to your mass times your velocity. So that's why we do the mass times the velocity for each thing. Now, the new thing for inelastic collisions is what the momentum looks like on the other side of this equation. So the equal sign is kind of like the collision, right? So the collision happens here. So you have a momentum before and after the collision. What's this look like on the other side of the equal sign in the final situation? Well, if you look at it, they're moving together, right? So you could still think of it as just one object. I mean, you could say P1, 2 because they combine. But let's go with the momentum of the first one plus the momentum of the second one again. Let's kind of derive the equation I'm about to show you. So we could do the same thing. The mass times the velocity of the block plus the mass times the velocity of the clay. And what does this look like? So this is M1, this is M2, but our final velocity is the same. That's the key. Since they stick together, we don't need to make a V1F and a separate V2F. That number, VF, is going to be the same for both. So we could just call it one term, just VF, plain old VF. Now we have a VF here and a VF here. So what we could do is rearrange our formula. We could call this M1 plus M2 times VF. We could take that VF out. You might see your math teacher doing that a lot, and rewrite it this way. And the beauty of that is if you look at the math, look what we just did. We're combining the mass together, just like we're combining the mass together over here. This is another example of where physics is using math to represent an actual real life situation. So you could kind of like visualize the mass. Visualize the physics Visualize the math is what I was trying to say. So you combine the masses and they're multiplied by the same velocity. So your equation now looks like this. You have two separate objects coming in initially, and then they combine together for one term. It's the momentum of them together. What is their momentum? All right, so that's the idea there. Okay, now we could use this equation. I'm just going to rewrite this one all the time for the problems on the sheet. Okay, so number 1 says a 2 kilogram mass is moving on a frictionless air track. So we'll call that M1. M1 is 2 kilograms. It collides into a motionless 1.5 kilogram mass. What is the combined speed of the two masses if they stick together on impact? It doesn't say it in the problem, but it actually shows you in the diagram the velocity of the first block, or the first cart, is initially 1.5 meters per second. And they tell you the mass of cart 2 is 1.5 kilograms. And the velocity of cart 2 initially is 0 meters per second. And we're looking for the final velocity of both carts, because then they stick together and they move to the right. So we'll see. So the initial momentum is equal to the final momentum, right? So the combined mass of both, the combined momentum of both carts is equal to the final momentum of the cart block system, M plus M. So the masses combined and they move off with some final velocity. This is M1 and M2, and initially they are separate. So we write them separately here. And now we can plug in, this is 2, this is 1.5 plus, this is going to cancel out to be 0 because it doesn't have any momentum, it's at rest. And this is 1.5 times the final velocity, which is what we're looking for. So you get 3, this cancels out, is equal to 3.5 times the final velocity. So the final velocity, VF, is equal to about 0.86 meters per second. You could round it. So that's the final velocity of the carts together. After the collision, you have this cart 1 with this guy sticking up here, and they're locked together and they're moving with the same velocity, VF. There is one thing we didn't talk about with inelastic collisions, and that's the conservation of kinetic energy. Kinetic energy actually isn't conserved, and I'm going to show it for these values. And now this one, I'm going to do the conservation of kinetic energy on that other sheet there. So we just showed that for inelastic collisions, momentum is conserved. The initial momentum of the whole system is equal to the final momentum. So momentum is conserved. But is kinetic energy conserved? That's what we want to figure out. So let's use the same data from that first question there. I'll write it out on the side. So we have the two carts with their initial velocities, and we calculated that the final velocity was 0.86 meters per second. Okay, so now we want to know, is kinetic energy conserved? Let's see. Before we did the initial momentum is equal to the final momentum. So that's saying that the momentum is conserved. But how about kinetic energy? Instead of the initial momentum, let's talk about the initial kinetic energy for the whole system, and then the final kinetic energy for the whole system. So we started with two separate carts. So we have KE1, the initial kinetic energy of the first cart, plus the initial kinetic energy of the second cart. Is that equal to, that's what we're trying to figure out, is it equal to the final kinetic energy of carts 1 and 2? Now, technically, they move together, so it depends on how you want to set up your formula. I think I'm going to do the move where we combine the masses together. So instead of two separate terms, I might have just KE1 plus 2 F. But, I mean, we could call it that if we want. That's fine. So if you remember, kinetic energy is equal to 1/2 mv squared. So this will be 1/2 times the mass of the first object times the velocity of the first object initially squared plus the same thing, 1/2 m2 v2I squared is equal to 1/2 the combined mass, m1 plus m2, times v2f. Sorry, not v2f squared, just vf squared, right? Because they move off the same final velocity. Now, if you wanted to, you could write it like this, but since they have the same velocities, that you just call it vf, and you don't have to separate into 1 and 2, it's the same. You could do that same trick where you take out the vf squared term, and then you're left with 1/2. Oh, you take out the 1/2 and the vf squared, and you're left with just an m1 plus an m2. So that's where this comes into play. So we could just write it like that. The math works out to the same way. You could try for yourself. So this is, we're just plugging in now, 2 times 1.5 squared plus, this is going to all cancel out, 1.5 kilograms times 0 squared, and then this is 1/2 the combined mass, 2 plus 1.5, times the velocity squared. Now, we're not solving for something here. We already know this is 0.86 meters per second, and we're going to square that. So what we're doing is seeing, is the kinetic energy the same before and after the collision? You might be surprised to find out that it's not. So this is 1.5 squared times 1. So you get 2.25 joules of kinetic energy. So the initial kinetic energy of the system is 2.25 joules. Because again, this is just 0, so all the kinetic energy is in the first cart as it's sliding along there, and the combined kinetic energy of when the carts are together is actually equal to 1.29 joules. Wait a second, this is not equal to, so the kinetic energy is not conserved. No. Kinetic energy is not conserved in an inelastic collision because it's not the same number on both sides, right? So what happened to this kinetic energy? As you could see, the kinetic energy decreased. During the collision, you lost some kinetic energy. That's kind of crazy. I thought that energy is supposed to be conserved, right? We did that law of conservation of energy thing. So shouldn't it be the same too? Remember, we're just looking at the kinetic energy. So what did we say for law of conservation of energy? Sometimes the energy transfers from one form to another. So even though you lost kinetic energy, you could have gained energy in other forms. So whatever this is, 2.25 minus 1.29, you have about 0.96 joules of other types of energy. Not Ke. This could be heat. It could be sound energy, the vibrations in the air. The deformation of any kind of material takes energy. So this is the reason why they say that energy is not conserved. The kinetic energy is not conserved for inelastic collisions. That's part of the definition of an inelastic collision, is that kinetic energy is not conserved. Now, this is a perfectly inelastic collision that we do because, as you could see, they totally stick together. You could have partially inelastic collisions where they do bounce off each other, and if you don't do the math, it kind of looks like a elastic collision because they bounce off each other. But how do we know it's inelastic? It's because if you do the calculation, kinetic energy is not conserved in those like partially inelastic collisions where they bounce off. So it looks elastic, but if you do the calculation, kinetic energy is not conserved. For all intents and purposes in this class, we're just looking at perfectly inelastic collisions where they stick together. So they're stuck together. Partially inelastic collisions, they don't necessarily stick together, but you could tell I'm just repeating myself here, but it's you could tell that they're inelastic because kinetic energy is not conserved. All right, back to the problems. Let's try number 2. 2 says a 2 kilogram blob of putty, so we'll call that the first mass, M1, is 2 kilograms, and it's moving, so V1I is 4 meters per second. And it slams into a 6 kilogram blob of putty at rest. So M2 is 6 kilograms. That's a pretty massive blob of putty. And it's V2I is 0 meters per second. What is the speed of the two stuck together blobs immediately after colliding? So they stick together, they're moving with the same velocity. What is that velocity? So you write down your equation. Initially, they're separate, so MV plus MV. Then they collide and their masses combine and they move with the same velocity. So this is the momentum of the first object initially. This is the momentum of the second object initially, and then they combine together and move with the same velocity. So this is 2 times 4 plus 6 times 0 is equal to 2 plus 6 times VF. This cancels out. You get 8 is equal to 8 VF, so the final velocity is 1 meter per second. All right, pretty good. Number 3, 2 blocks moving in opposite directions collide and stick together after the collision as shown in the diagram. What is their combined speed after the collision? This is a tricky one. So M1 is going to be 1 kilogram, and its initial velocity, V1I, is equal to 8 meters per second. M2 is equal to 2 kilograms, and its initial velocity is 1 meter per second. But did you guys catch the trick? It's moving in the opposite direction. This is to the right, so it's positive. This is to the left, so it's negative. We have to make it negative to show that they're going to collide into each other. If we made it positive, then it would look like they're going in the same direction, and the total momentum would be greater. Since they're moving against each other, the total momentum is going to be less than what it would have been. So the velocity is what we're, so we have to make this negative, all right, because it's going to the left. Technically, they don't have to show the negative number here. They're using an arrow instead of using the negative sign. We're looking for VF. So we could write our equation. We substitute in the numbers, and now we can solve. So 1 times 8 is 8. Minus 2 is equal to 3 times VF. So you get a 6 is equal to 3 VF. And 6 divided by 3 is 2. So the final velocity is 2 meters per second. Okay, number 4. A 3,000 kilogram truck, so M1 is 3,000 kilograms. It's moving rightward with a speed of 5 kilometers per hour, so V1I is 5 kilometers per hour. And it's colliding head-on with a 1,000 kilogram car, so it's less massive. It's 1,000 kilograms. Moving leftward with a speed of 10 kilometers per hour, so V2I is negative 10 kilometers per hour. Again, it's negative because you're going left. They're in opposite directions. The two vehicles stick together and move with the same velocity after the collision. Determine the post-collision speed of the car and truck. So you're just looking at the velocity, final velocity. That's what we want to know. Again, so you write down your equation. Oh, first of all right. You might want to put this into meters per second, and you definitely can. I'll show you how to do it. But you don't have to for momentum type problems as long as you're consistent. If we're looking for VF and we report our answer in terms of kilometers per hour, the units still work for that. The problem comes into play if you try to use this final velocity and it's like, okay, what's the kinetic energy? Well, kinetic energy is in terms of joules, and you would need a meter per second to have the units agree so that you get answers in terms of joules. So it's good practice to change it into meters per second, but technically for momentum type problems, you don't have to. I'm not going to in my equation, I'm going to leave the numbers, but I'll show you how to do it. It is good to know, so you could skip past this if you'd like. Just so you know, this is 5 kilometers per hour. I like to write it like that when I'm converting units because I'm going to multiply by a conversion factor. And we want our units to cancel out. So let's get rid of the hours. Hours, it's on the bottom here, so let's write it on the top. And we want to convert into seconds. Do you know how many seconds are in an hour? If you do, you could write seconds. If not, you could write minutes. And so 1 hour is equal to 60 minutes. And that'll give us an answer in terms of kilometers per minute. So we have some more work to do here. We want to get rid of the minutes, so write it on the other side of the fraction there. And want to go into seconds. So we got to do 1 minute is equal to 60 seconds. And the minutes will cancel out, and we'll be left in terms of kilometers per second, which is pretty good, but we want meters per second. Now, you could have also done hours per second. So 1 hour is equal to 60 times 60. That's 3,600 seconds. So typically I'll do 3,600 seconds is equal to 1 hour. And so I put the time, I want it in seconds, so that's good. And I multiply by, well, I want to get rid of the kilometers. It's on the top, so I'll put it on the bottom so that the kilometers cancel out. And I want to get into meters. And you can look in your reference table. It tells you for the prefix kilo, that's 10 to the third. And what that means is 1 kilo anything is equal to 10 to the third base units. So in this case, 1 kilometer is equal to 1,000 meters. And since these two numbers are equivalent, when you divide them, you're left with 1. So it's like you're multiplying this quantity times a 1. You're not changing the magnitude at all. What you're doing is you're changing you're getting rid of the units. So you're left with an answer in terms of meters per second. So you get 5,000, 5 times 10 to the third, divided by 3,600. So you get an answer of 1.39 meters per second. So you go 1.39 meters every second if you're going 5 kilometers per hour. But that's kind of annoying to use. I'd rather just use a nice number like 5. And since we can use that in our momentum equation because the units will agree, I'm just going to do that. But you know, this looks like a lot of work, but for me it's not that bad because I've done it so often. If you practice this, it's a good tool to know. You should know how to convert units. It's not always just, oh, do I multiply or divide? By doing it this way, you set yourself up nice and you'll know how to do it every single time. Anyway, let's write the equation down. Let's substitute it in our numbers, making sure that we make V2I negative 10. So this is 3,000 times V1I is 5 plus 1,000 times V2I is negative 10 is equal to 3,000 plus 1,000 times VF, which is what we're looking for. So now you have 15,000 kilogram meters per second, or sorry, kilogram kilometers per hour. That's the momentum of the first car, plus negative 10,000 kilogram kilometers per hour. That's the momentum of the second car, is equal to 4,000 times VF. So you get 5,000 divided by 4,000, and VF is equal to 1.25 meters per second. You get a positive number, so that means that the truck wins basically, and they slide off to the right before coming to a stop. Number 5 says a 1,000 kilogram car. So M1 is 1,000 kilograms. So it's a 1,000 kilogram car. It's rolling down the street at 2.5 meters per second. Maybe somebody forgot to put their parking brake on, or maybe somebody's ghost riding it. How fast would a 2,500 kilogram car have to collide into it in order to bring it to rest? Do not ghost ride any cars. It's a stupid thing. And don't have your friend smash into your car in order to stop it. either. So how fast does this have to be in order to bring it to rest? Now that should be a keyword. We've seen it before. If you're at rest, your velocity is 0. And we want the final velocity to be, you're colliding it into each other, and then you're making your final velocity 0 meters per second. So this is a little bit different from the other ones, because now we're not looking for the final velocity. We know what it is. You're bringing it to a rest, and you're saying, how fast would this car have to be? But you could still use the same equation, and you could carefully substitute in your numbers, and make a note that now the variable is here. Actually, I wrote it wrong because I was going too fast. We know what VF is. It's supposed to be 0. So that means that your final momentum should be 0 kilogram meters per second, which means your initial momentum should also be 0 kilogram meters per second. That's what the total momentum is. So you have 2,500 plus 2,500 V2I is equal to 0. And what you might see some people do, and this is valid, they'll start with their equation being, okay, the momentum of the first car is equal to the negative momentum of the second car in order for them to cancel out. And this is where that equation comes from. Sometimes you'll see M1 V1I is equal to M2 V2I, but they make a negative sign here. Looks like 3. Okay. They'll say, okay, if you want the final momentum to be 0, this equation must be true, that this is equal to the negative of this, because they should cancel each other out and become 0. That's a totally valid equation. You can do that, but the way I teach like the thing that will work every single time. And if you want to come up with your own shortcuts, that's totally valid too. You just have to make sure that they work every single time, or only apply them when they work. So this is going to be V2I is equal to -1 meter per second. So if the first car is going at 2.5 meters per second, the second car has to go in the opposite direction, and it only needs to go at 1 meter per second because it's more massive than the other one. So in order to have the same momentum as the other one, you just have to have a smaller velocity, 1 meter per second. Okay. Number 6 says a railroad car with a mass of 4,000 kilograms, so M1 is 4,000 kilograms, is traveling with a speed of 2 meters per second, so V1I equals 2 meters per second, and it slams into another railroad car with a mass of 6,000 kilograms, so M2 is 6,000 kilograms, and couples together as shown in the diagram below. So I guess that the second one is initially at rest. V2I is 0 meters per second. Does it say it in the problem? It doesn't really say it in the problem that the second cart is at rest, but you can see in the diagram that they're showing that it is. So it says, what is the combined speed of the railroad cars after the collision? So they lock together and move with the same final velocity. What is that final velocity? Okay, so we're just going to plug in the equation, and you substitute in your values. And now you could solve. So this is 8,000. This cancels out, is equal to 10,000 VF. So VF is equal to 8/10, or 0.8 meters per second. Okay, that's good. Number 7, a large locomotive with a mass 4 times that of the smaller motionless railroad car collides and couples together. The larger locomotive is traveling at 5 kilometers per hour before the collision, and the smaller railroad car is initially at rest. What is their combined speed after the collision? Okay, this is the most requested question on the homework, so you might have skipped right to this spot. So let's write down the givens, but now it just says it's 4 times that of the smaller motionless railroad car. So they don't tell you how many kilograms it is, but they're giving you a hint of one way that you can solve for this. If you let the mass of the smaller one and be called M, just capital M, then this other railroad car must be 4 times as big. So 4m. So we're going to do the same process. We could call it m1 is equal to the more massive one. So it's 4 times as massive as m2, which we're just deciding to call m. So one is m, the other is 4m. That's a trick, right? So that's the trick for the problem. It's like a way to solve for it. Alternatively, you could have just said, okay, let's let the mass be, maybe it's 1,000 kilograms. And maybe the other car would be 4,000 kilograms then. More, maybe it's 40, 10,000, whatever it is, or maybe it's 1 kilogram and 4 kilograms. You could set it equal to just anything, any mass that you want, and as long as the other one is 4 times as big, it'll work out just fine. But I'll show you why. So I'll use the variables, and I'll show you why the mass doesn't really matter, because they kind of cancel each other out. So V1I is equal to 5 kilometers per hour. And I think it was the previous video where we said, okay, for momentum, you could actually leave it in kilometers per hour. It's not going to affect your units at all. As long as you report your answer in terms of kilometers per hour, the units all work out. You run into trouble, though, if you try to calculate the kinetic energy. So kinetic energy is in terms of joules, which is in terms of meters per second. So that's not going to work out. So V2I is 0 kilometers per hour. We could just leave it like that and we wouldn't have to convert. So we're looking for VF. What is their combined speed? So we set up the equation and now we could plug in our numbers, but for M1, we're calling it 4M. Just leave it like that. This is 5 kilometers per hour plus M2, we said is just M times V2I is 0, it's at rest. And then you have a 4M plus an M, and you have VF. So this cancels out. You're left with 20M. Some people were having trouble. It's like, oh, can you do that? They're not like terms, right? I'm not sure. Can you combine those two things? Well, you can't add or subtract unlike terms, but you can multiply and divide, because for multiplication, this is saying it's 4 times m times 5. And you could rewrite that. So 4 times 5 times m, which is the same. 4 times 5 is 20 times m. So you could rewrite it that way too. Some people were asking me about that. They're not really sure about the combining the like terms, that type of thing. When you're multiplying, you could definitely multiply unlike terms. So this would be 20m is equal to, and these two terms are like terms. So you have a 4m plus another 1m. So you could combine those. That's a 5m times vf. So now we want to get vf by itself. That's the goal. So we want to divide both sides by 5m. And what you'll notice is that the m's cancel out. You have an m divided by an m. Any number divided by another number is just 1. So you have 20 over 5 times 1. So that's why they cancel out. So 20 divided by 5 is 4. Kilometers per hour is equal to VF. That's your answer there. That was a tricky one. Again, if you plugged in a random number for m, maybe even 1 kilogram, and this is 4, you'd get the same answer because the masses cancel out. Okay. Number 8 says, during a goal line stand, a 75 kilogram fullback moving eastward with a speed of 10 meters per second. So we'll call that m1 is equal to 75 kilograms. The velocity of the first one initially is 10 meters per second. And they're colliding with a head-on with a 100 kilogram lineman. So m2 is equal to 100 kilograms. And that lineman is moving westward with a speed of 4 meters per second. If you got this one wrong and you skip to this video, skip to this question, it might be because you didn't make it negative. It says it's moving westward. They're moving against each other. So you have to make one of them negative to show that they're going in opposite directions. And since this one's going west, we'll make that one negative. The two players collide and stick together, moving at the same velocity after the collision. Determine the post-collision velocity, so VF, of the two players. So, okay, that was the trick. You had to make sure that you make that negative because their momentums are going in different directions. This guy's going this way. The other guy's going this way. So this is the negative velocity. So you write your equation. You substitute in your numbers. So times 10 plus 100 times -4 is equal to 75 plus 100 times VF. And now you could solve. 750 minus 400 is equal to 175 VF. So 350 is equal to 175 VF. So VF is equal to 2 meters per second in the positive direction. So that means that this guy who was moving to the right actually was winning the collision in terms of momentum. So they start moving to the right. Okay. Number 9 says, in a perfectly elastic collision, a 0.25 kilogram cue ball moving at 2 meters per second strikes a stationary 8 ball of equal mass. What is the velocity of the 8 ball after the collision if the cue ball remains stationary after striking it? And they give you the nice data right here. So that's what we're looking for. Now this is elastic. They do not stick together. So we're going to use that equation that we used in 9.3. So the mass of the first ball is 0.25 kilograms. And the second ball is of equal mass. And the initial velocity of the cue ball is 2 meters per second. The initial velocity of the 8 ball is 0 meters per second. It's at rest. And V1F, it says the cue ball remains stationary after striking the 8 ball. And how fast is the 8 ball going? That's the question. So now you're going to write your equation again, but they are separate. So you need 2 separate things on each side of the equation. You have the momentum of the first ball plus the momentum of the second ball before the collision is equal to the momentum of the first ball plus the momentum of the second ball after the collision. So this is for 1, 2, 1, 2, initial velocities, final velocities. So back to this equation here, we're no longer putting this in terms of M1 plus M2 because they're not locking together. They're bouncing off each other. It's elastic. It's an elastic collision. So this is 0.25 times 2 plus 0.25 times 0. So that cancels out. Is equal to 0.25 times 0 because that's cue ball is now at rest times 0.25 times V2F. And by looking at it, and you might have even known already what's going to happen, these things cancel out, right? They both cancel out on either side. So you're just left with 0.5 kilogram meters per second is equal to 0.25 times V2F. You divide both sides, and V2F is going to be 2 meters per second. You could have predicted that. How could you have predicted that? Well, they're of equal mass, right? So that means that when you do the momentum, this guy has all the momentum, but then it doesn't have any more momentum. This guy didn't have any momentum. So that means that the second ball must have picked up all of the momentum from the first ball. And since they're of equal mass, that means their velocity must have been the same. And that's about it. All right. Have a good day.